While this is switching over, I'll steal the microphone to say one last comment on the last section, which is, I think one other interesting thing as we're looking at combining is asking ourselves what it's for. Because if what we're looking at is relative yield changes, there may be some differences between the global and the regional that are actually less important if their response to climate change is more consistent. Food for thought, and now I'm going to shift into climate. So I have a very short time here to go through what is, of course, a very big topic. I'm going to try to update people in the room about where AgMIP is in many of its climate activities now, and then I have some proposals for the CGRA up for discussion this week. So the first thing, of course, is that there's this continuum that we've heard about throughout this week of periods of interest within the climate, as the climate goes forward. And I'll just very quickly go through some of these. Prior to 1980, I'm not sure how much work we're going to be doing. There's a lot of uncertainty in observational networks and data loss over the years prior to 1980. So a lot of times when we're looking at historical validation, we're going to be focusing on the satellite era, where we have improvement in observational coverage, reduction in uncertainty, particularly in areas where there was low observational density in terms of the stations. And that is true in many developing countries and agricultural regions. In this near term that we've talked about a lot here, the challenge here is that climate variability really does dominate over the climate change signal in the next kind of 20 to 30 years. And this is a problem because there really is a low skill in prediction. And I'll get at the end here some ideas of what we can actually do in that period. But we have to be very careful thinking that it is the same type of physics and predictability and skill in what we have later. Now, the mid-century becomes an interesting time period because the climate change signal does begin to emerge from climate variability. And then by the end of the century, we really see differences between the RCPs. The mitigation regimes have started to separate out the climate signals. And of course, we have to remember that time doesn't stop in 2100, despite many IPCC charts stopping in 2100 and many other publications. I don't think we're going to get much past 2100 in this project just because the societal scenarios and the economic simulations running out that far. From what I've heard from the economists, really, they don't want to touch that right now. There's a lot of uncertainty as you get that far out. So let's start by looking at this historical period because climate data sets in this historical period allow us to do sensibility analysis, which is my new favorite buzzword. How can we show that these models really are capturing the main features of these systems? The other thing, of course, about the historical period is once we start talking about downscaling, most downscaling methods are either built upon the historical period or trained upon the statistics of the historical period. So it becomes very important what we select. The product that we've been working on mostly in AgMIP is something called AgMIP, which is based on the NASA Modern Era Retrospective Analysis for Research and Applications. It's a product that basically takes all the observations it can get its hands on and merges it using atmospheric physics and other pieces of information. Now, a lot of information on here. What I'll point out is that where this really came from was I was repeating the same process again and again. Somebody would come to me saying, I have an observational data set that I want to use for agricultural models, and I have a 15-year gap, but I have data around that, and I don't really know what I should do. So I was again and again saying, well, let's look at what the MERA or other retrospective analyses say for that time period because they have global coverage. And then I realized that even MERA has its own problems with solar radiation, some of the mean biases. So this ends up being a combination of several different products, satellites for solar radiation and rainfall, gridded data sets like CRU, and other information all is merged together. And this was something I was repeating again and again, so eventually we just did it over the whole globe. And comparing against many of the other data sets that are similar to it, the main thing I want to point out, I think this pointer works, main thing I want to point out, this is correlation with daily rainfall. And because of this one MERA land product that we incorporate here, this blue line, which is AgMIP, actually is head and shoulders ahead of all of the other climate data products in terms of actually capturing day-by-day rainfall events around the world. Now, there's also information that comes in that allows us to have a much better threat score of extreme events. This basically being higher numbers, as you can see, we have 3 columns here, but on any one of the columns, you'll see that there's an improvement over these other data sets. this shows that we're actually capturing not just that rain events do occur in some distribution, but the actual time that they did occur. So we do believe that there's some benefit in using this approach, but in a minute I'll tell you some reasons we also have to be careful about it. The reason this is important is there's all these different data sets that represent this 1980 to 2010 period, and unfortunately there's a lot of differences across. This is anomalies, and you'll see some places you'll see large percentage differences between these data sets. So this is not, even though we have all these historical observations, there's still uncertainty here, and it's going to affect how we validate, how we calibrate our models as we go forward. Now, we've been working with this. Actually, the GCMI have taken all of their crop models and run them through, you see some very clear benefit. Actually, this is just the PDSAT model. I was working with Joshua and some of his students on this. And you'll see if we use just an uncorrected reanalysis, this CFSR is the NCEP reanalysis. These green areas here show high correlation, but when we do this kind of ag CFSR, this same correction that we did for AgMIP, when we do that, you can see a much bigger improvement in correlation between the maize simulation and the actual observations of maize yield. So we do believe there's benefit to this. We're using it to look at the actual sequence of extreme events in the United States, showing what we can capture in our models and what we can't. So we're doing a lot of work on this. But we can take this to the global level. When we run all of our crop models through with different data sets, you see that there are differences. And I'll just point out as an example, here's AgMIP in Australia has a pretty high correlation, whereas some of these other ones do not. And likewise, I could find places where AgMIP does worse. I don't mean to just be trumpeting this, but there are differences in the historical data sets that you use that translate all the way into the fidelity of the crop model outputs that come out. So this is something that we're working on, trying to figure out what we can actually do. Now, as we get going forward into climate scenarios going into the future, one thing that we're going to see, I think, as we get into the breakout sessions and further on this week, there are far too many combinations for me to get my way and run all GCMs, all time periods, all RCPs. By the time we count up adaptations, SSPs, different crop models, different economic models, the combinations become astronomical. So I'm going to start, I've been battling over the years to keep this number at least 5 GCMs that we include. But what I'm going to show here now is a way that we've actually been selecting 5 GCMs for particular regions based upon the overall distribution of GCM projections for that region. So the idea is we're going to look especially at temperature and rainfall within the growing season. I know that there's many other variables, but this is a kind of very good starting point to look at. So I'm going to set up a chart here. I'm going to build this chart to show you how we're doing this. The main idea here, this is Ames, Iowa. I'm eventually going to be showing. So I'm looking at May, June, July, August, September, kind of a growing season there. And on the y-axis is the precipitation change. And then on the x-axis is the temperature change. So the main thing is there's 5 types of relative change. There's kind of the middle of the ensemble of projections. There's the relatively cool and wet, the relatively cool and dry, the relatively hot and wet, and the relatively hot and dry. If we can capture and sample from these 5 quadrants, we're going to have a pretty good idea of what's happening. All right, so here's Ames, Iowa, and this is the actual GCM projections. You'll see this cloud. There's some correlation in terms of, it looks like hot and dry versus cool and wet. And we have 29 different CMIP 5 GCMs. This is mid-century RCP 8.5. So if we actually do the statistics of this distribution, you'll see that the median is a slight increase in rainfall and a temperature change of about 3.2, 3.3. But then we can actually create this middle section by taking 1 standard deviation across. And I have a paper right now I'm writing where I justify why it's 1, not 2, and things like that. I have to just emphasize again, when I say cool, that does not mean colder than present. It means relatively cool as we go forward. But we can then take all of these GCMs and say which quadrant do they fall into. And then we can look within each quadrant and say, okay, if I wanted to pick a representative green model or a representative orange model or red model, how can I do that? So the easiest thing to do is you actually take the center of mass for these and each one, and we get this dot that points us towards potentially a representative model. So here is the models that we would select in this case, the models that are near those dots. So this ends up taking an assumption that the models are equally likely, but we can kind of cluster them in this simple way and take representative models. And then, of course, we can remember how many models fell in each quadrant and pass that information down the line as an uncertainty measure so that economists who might find really big results in these two quadrants know that there's actually a much more likely chance of this quadrant happening than this one. All right, so then we can pass these all the way through. So this is one approach, and it's interesting actually because then we can recreate GCMs over the whole world by saying which quadrant does any grid box fall into around the world. So here I think I just took the annual so to make it simple, but you can see the GISS model, the NASA GISS model, tends to have a lot of greens and blues. It's relatively cool compared to the overall scope of GCMs. Whereas the Hadley model here, you see a lot of yellows and reds. But if we were to actually do this analysis, we could recreate the global simulations in this way. So how have we actually been doing this in terms of the creation of the future scenarios? I realize I'm running out of time here. We've used something called the enhanced delta approach, which basically takes the distribution of observations and shifts them to make it look more like how the GCMs say the climate is changing. Okay? The simple delta approach, people may know, you just shift the entire distribution all at once. This enhanced delta approach allows the extremes to change more rapidly than the median or less. So we've been doing that. I won't belabor the details given the time. Of course, there's many other approaches. There's dynamical downscaling like the Cordex experiments. There's some challenges there in consistency and coverage. I'd be happy to talk to anybody about my reservations there. There's also a lot of statistical downscaling approaches. AgMIP has been using one of these. There's also now the NASA Earth Exchange, which has run many different GCMs. This is kind of the opposite. You're actually taking the GCMs and shifting them to look more like observations. And there are strengths and weaknesses to that approach. I'll also just point out that there's been a lot of this done on a monthly timescale, and only relatively recently have people been doing this on a daily timescale, and that brings challenges in. And I'll also just mention there's empirical statistical downscaling, which at this point just is not as universally covered as some of these other approaches. Okay. I promised I would say something about near-term scenarios. This is an approach that I've been developing along with Arthur Green at the IRI. And the basic idea here is you can statistically disaggregate historical climate to get an idea of the natural variability. And then you can use the uncertainty in the GCM projections to go forward and give some kind of probabilistic approach of what various extremes might look like. So in this case, we're looking at Diorbal, Senegal. This was a run we did in West Africa. We ran 10,000 different versions of the future and picked out the 5th percentile, 50th, and 95th percentile of rainfall in the 2030s. And then what you see here is the greens are the wet, the browns are the dry, and the blues are kind of the average, which actually ended up being kind of dry at the beginning and wet at the end, interestingly, on that decade. And then the shading here is the difference in the GCM trend. So what you can see is it doesn't really matter what the GCMs do in terms of the overall rainfall trend. When you get an extreme year, that extreme year can overwhelm some of those other things. And you see that all the way across. So this is the type of thing, it's not a prediction, but we can use this as a kind of sensibility analysis, creating scenarios that we think might be about the type of extreme people will be looking at.
Alex, could you do that retrospectively, looking back and just say the last 10 or 15 or 20 years, you know, using that type of statistical or modeling approach and what that would have looked like then?
Well, we could certainly hindcast. We could do the statistical regression only before 2000 and then run from 2000 forward. But again, this isn't a prediction. I guess if we did it over the whole world, we might start to get to significance in terms of we should see some 95th percentile event somewhere, but that's a little bit beyond the scope of what we're doing here. But certainly there will be potential to analyze these. Okay, so this is getting to my last slide. Here's some starting proposals for CGRA climate. So I've put out a lot there. Let me put some straw men, actual decisions on the table and let people react. So we talked about this the other day. I believe, have to start with CMIP 5 outputs rather than wait for CMIP 6. I think the 1980 to 2010 period forms a suitable baseline for our validation and calibration because we have a combination of climate data and even some ag sector data is a little bit more dense for us to validate with. I'll also argue that the mid-century, the kind of 2040 to 2070 period, you could also call that the 2050s as the central decade, provides this sweet spot where we have a climate change signal and some plausible idea of what some scenarios might look like. So if we, as we're whittling down time periods and scenarios and all these things, I might push towards the 2050s. Second, I actually am going to suggest that we begin with either the AgMIP or the next climate approach, rather than trying to scale up this AgMIP approach that we've done in some places, because it is very well established around the world. AgMIP is being used for many other sectors that people will probably want to take our results and compare against. They have already created many of these data sets that will be easy for us to use and justify. The other thing that's nice about that is that we could do a comparison with the historical period to get an idea of the differences and potential uncertainties within those. That said, we are not going to give up using the best possible local data when we're doing site-based models. This is one of the benefits of doing site-based modeling, is that you can use true observational data. So in that sense, we can do this for comparison. And then if we're making future climate scenarios with that improved data, we use the same statistical method that was used by NEX or AgMIP, so that we have a methodological consistency even as we go into the future. Next, we also can use regional analysis to determine the GCM subsets. So that same thing about hot, dry, and cool, wet, we can do that to pick which NEX or AgMIP scenarios we want to use, which GCMs are of most interest. And then we can build this international picture using representative quadrants. And finally, when we're doing extreme events, we are going to have to rely on sensitivity analyses and scenarios rather than expecting predictable or predictions, let's say. And again, there's some justification there, but we could potentially associate probabilities using that near-term scenario approach I mentioned. So with that, I'll stop. Thanks, Frank. Oh, quick, yeah.
That is possibly relevant for more than the people interested in climate.
Yeah.
You and a few others in this room know a lot about bias correction, and it's generally accepted that you have to bias correct global climate model results to have reasonable data to work with. And Ken just mentioned that the maze models are basically the slope of the response is independent of calibration. How would you assess the potential to bias correct global gridded crop model results?
Well, interestingly, that's actually the comment I stole the microphone for at the beginning, is I actually think if we can show that the key response is more consistent than the mean bias, and we've looked at this in the wheat, maize, rice, all these pilots have, I've at least tried to bring this up. There is some reason to believe that we might have useful information even given the bias. And of course, that is similar to what you have in the climate scenarios, because the climate models really are designed to get climate change. And the mean conditions are a kind of sensibility analysis, show us that we have some major purpose there, but they're really driven to get that change signal. And I think if we use the models in that same approach, and if that satisfies what the economists need, we might find a lot more room to grow and go forward with that. Yeah, and some of the same methods also we should explore using.
Just on CMIP 5 versus CMIP 6, I was wondering, and since many of our studies end in 2050, whether there are going to be big changes, whether we anticipate big changes before 2050 or more after 2050.
I would argue there won't be huge changes. I mean, between CMIP 3 and CMIP 5, there was not new, completely ground-breaking shifts in regional climate or overall climate sensitivity. I would expect added detail more than anything else. So some of the subnational information potentially could improve. And there may be, I mean, you don't know until they do the runs, obviously. I may be mistaken. But there's going to be a tremendous increase in resolution of those models. And it's possible that some of those physical features will shift. I don't know if, Brian, you have a comment on that as well.
Are we entering into discussion?
Yeah.
Well, just a comment on
Quick comment.
CMIP 6 is that, well, I totally think, yeah, you could focus on CMIP 5. It may be useful to, in selecting scenarios to run, to have at least some overlap. Only a few scenarios will be run in CMIP 6, not the whole matrix. So depending on which ones are chosen, you may end up with no scenarios run in this assessment that will actually have climate simulations in CMIP 6. So it may be useful at least one, something like that.
Is there a breakout plan for around the climate scenario specifically in the course of the...
I'm not sure.
Okay, Jim.
Well, I was just going to comment On this sensitivity analysis, the last one there, I still think that these climate extremes are really important. And it's true not only now, based on what Jerry was saying, looking at history, but also the nearer term and in the longer term as well. So I was wondering if you had that in mind here. Are you talking about only sensitivity analysis in the 2050 schedule?
Oh, you mean extreme events going out that far? Yeah, I mean, yeah, that's an interesting point, actually. I mean, a lot of my own personal work these days is looking at the interaction of variability or extreme events and mean climate shifts. So I'm definitely interested in that. We've only done this near-term scenario out to 2050, but there's nothing saying we couldn't continue it beyond that. I think some of those shifts, they will appear within the next and the AgMIP model approach. We will see shifts in annual variability, but I still think a lot of that, when it comes down to it, we need to, if we were doing any other system, we would go to the stakeholders and say, what are the types of systems you're interested in, or the types of extreme events that are interesting to you, and then we would go into those models and try to establish whether the probability is increasing or what.
I'm thinking more of the nearer term than the longer term.
Yeah, so you're saying even shorter.
Even shorter,
Yeah.
between now and
Okay.
Because that's what the policymakers.
Yeah.
Good.